Every year, over 100,000 kilometers of new railway tracks are laid worldwide, enough to circle the Earth several times. But few people stop to think about how a perfectly straight strip of steel, capable of withstanding the weight of multi-ton trains and speeds of over 300 kilometers per hour, is born from a piece of scrap metal. Inside furnaces, the temperature reaches 1,500 degrees Celsius. Molten metal flows like solar lava, and precision is measured down to tenths of a millimeter. And most importantly, there is a secret here that is rarely shown publicly. If you watch until the end, you'll learn this secret that allows rails to last for decades without a single joint.
First, a steel mixture needs to be made. Scrap metal, iron ore, coke, and limestone, the raw materials that will become the future rail, are fed into the furnace. The temperature in a blast furnace reaches over 2,732 degrees Fahrenheit. Under this infernal heat, the metal becomes liquid, acquiring the color of the red-hot sun. Workers carefully monitor the composition. Even an extra 0.1% of carbon can make the rail brittle or too soft. After melting, the molten steel is poured into molds, metal ingot molds that form rectangular blocks called ingots or slabs. They don't yet look like a rail. They are just bars several meters long, over 30 centimeters wide. After pouring, each such blank is cooled, but not completely. It is kept warm to reduce the load during rolling.
This stage is the foundation of everything. If the steel is of poor quality, even perfect rolling won't save the situation. So control here is almost a ritual. Chemists check the composition, metallurgists control the temperature, and automatic sensors record the uniformity of cooling. And only when everything matches down to the last parameter is the blank sent further, into the fiery furnace of the rolling mill. In the rolling mill, massive bars, up to 20 meters long, are heated in furnaces to a temperature of over 1,200 degrees Celsius. The metal becomes plastic, like dough, but retains its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce the thickness, then to give it the correct shape.
Each pass involves compressing and stretching the metal, which gradually transforms from a simple bar into a future rail with a complex cross-sectional profile, with a head, a web, and a foot. To achieve precise geometry, finish calibration rolling is used. This is like the final polishing of the shape. The tolerances at this stage do not exceed 0.3 of a millimeter. Immediately after rolling, the rails, still hot, undergo a cooling process. They are evenly blown with air or left to cool in an open area. It is important that the cooling is symmetrical, otherwise the metal may warp. To ensure a smooth, impact-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding.
In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, formed as a result of the reaction of powdered aluminum with iron oxide. The temperature reaches as high as 2,500 degrees Celsius, is poured there. This melt penetrates both parts of the rail and envelops the joint zone. When it solidifies, a monolithic joint is formed, stronger than the rail itself. After this, the excess metal is cut off, and the weld site is ground to a perfectly level surface without any protrusions. Every joint is inspected, with ultrasound or eddy currents, so that no hidden microcracks remain. Such long rails are easier to transport than it seems. They are wound onto special drums or transported on platforms with swivel nodes.
And at the construction site, the sections are joined again, this time by welding or using special bolt joints. The result is a rail string that stretches for kilometers without a single click. The same silent glide that we are used to taking for granted on high-speed trains. But first, after rolling and welding, the rails are still alive. Stresses remain inside the metal, and the grain structure needs stabilization. This is where heat treatment comes into play, which gives the rail strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, about 1,832 degrees Fahrenheit. This is done in furnaces up to tens of meters long, where the temperature is controlled with degree precision. At this point, the crystal lattice of the steel transitions to a new state, austenitic. But the main part begins after.
The rail is instantly cooled. Jets of water under high pressure are directed along the head and web, the very part on which the wheel rolls. The temperature drops in a flash, and a martensitic structure forms in the metal, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled again. This balances the structure, relieves excess internal stresses, and ensures that the rail will withstand both frost and heat, and thousands of trains a day. As a result, the metal holds its shape and withstands a pressure of tens of tons per square inch without deforming. Before the rail hits the road, it goes through a whole series of rigorous tests, as if it wants to join the army of high-speed transport. In special laboratories, it is tested for strength, hardness, geometry, and internal defect.
First, ultrasonic inspection. High-frequency waves are sent into the rail. If there is a micro crack or a void somewhere inside, the signal is reflected and reveals the problem. Then, hardness measurement along the entire length to ensure that the heat treatment was uniform. In parallel, the straightness and profile are checked. Laser sensors scan every inch, detecting even minor curvatures that could cause vibration or wear. And finally, a bending and impact test. A fragment of the rail is loaded with a pressure tens of times greater than the weight of a train to make sure it will withstand any challenges on the route. When the rail has successfully passed all the tests, it's time for the most responsible journey to the installation site. But how do you transport giant metal strips over 90 meters long? Ordinary trucks can't handle it. Here, special railway platforms with curved supports are used, which reduce stress and prevent the rail from sagging or vibrating during movement. Sometimes rails are transported already welded into even longer sections of 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is necessary to compensate for the thermal expansion and contraction of the metal. Otherwise, in the heat, it will buckle, and in the cold, gaps will form. In practice, each rail is laid taking into account these physical changes. Usually, this is a point of no thermal stress.
Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen, as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems known as Christmas trees that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. but this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life, powering the modern world. Are you ready to peer into a world where millimeters determine life and gleaming metal journeys from raw material to lethal precision? Picture this. Over 12 billion cartridges are manufactured worldwide every year for military, police, hunters, and sportsmen. And each one is the result of jewelers' precision engineering, where temperature, pressure, and form matter down to the last decimal place. In this video, we'll show you everything from selecting gunpowder and brass alloys to quality tests where muzzle velocity reaches nearly 900 meters per second. Brace yourself. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the very edge of what's possible. Hundreds of millions of cartridges roll off factory production lines worldwide every year, and each one passes through quality control with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive coils roughly 1.5 millimeters thick, weighing up to 2,700 kilograms. These coils are supplied by metallurgical plants. Upon arrival at the factory, the brass is unwound on a special platform and fed into a rolling mill. The metal's temperature at this stage reaches 315 degrees Celsius to make it more malleable. Next, the brass sheet is fed into a press line, a high-speed stamping machine that cuts out discs with lightning precision, so-called blanks. Their diameter is roughly 19 millimeters. The press operates at up to 250 strikes per minute. The resulting discs are heated to 430 degrees, essential for the next deep drawing process. They're immersed in lubricant and fed into a hydraulic press, where under pressure of up to 100 tons, the disc is formed into a primary case. This process repeats several times, each time drawing the case slightly longer and thinner. Each case after drawing is annealed, heated to 540 degrees to relieve internal stress in the metal. Otherwise, the case could crack during firing. It's then cooled in water and cleaned in an acid solution. Next comes calibration and weighing. Cases pass through a high-precision laser control system. Weight discrepancy means automatic rejection. Length, wall thickness, and even acoustic response are checked. Special sensors detect whether there are micro cracks in the case. Finally, the case is trimmed to precise length, a groove is cut for the primer and the neck is expanded. The next critical stage is primer installation. It's a small but absolutely vital component that initiates firing. The primer is miniature explosive. Inside a metal cup sits the primary detonator, typically based on lead styphnate. Before installation, primers are tested for sensitivity. On an automated line, each case passes through a priming station, where a mechanism inserts the primer into the rear of the case with incredible precision. Next comes gunpowder. The type depends on the cartridge's purpose. On average, one 223 Remington cartridge contains roughly 1.5 grams of powder. For comparison, a .45 caliber cartridge uses just 0.4 of a gram. Powder is measured automatically to 1/1000th of a gram. Excess or shortage means danger for the shooter and weapon. A 1/10 of a gram discrepancy is unacceptable. Once the powder's in, it's time to install the bullet. Its material, shape, and mass depend on the task: hunting, military, sport. But installation happens with the same precision. The bullet is pressed under pressure into the case. Then the neck is crimped so it won't cop out during chambering. After this comes final calibration and visual inspection. Rejection rate at major facilities is under 0.3%. And only after all stages of inspection, calibration, and final weighing does the cartridge reach its ultimate phase, packaging. Packaging isn't just aesthetics, it's a matter of protection, identification, and logistics. Cartridges are automatically sorted into trays or fed to weighing lines, where batches are formed in 20s, 50s, or 100s. The cheapest option is plastic trays with heat shrink film. Military supplies are packaged differently, in zinc or steel containers with hermetic lids. Inside are inserts with anti-corrosion treatment, marking with caliber, batch number, and manufacturing date. On industrial lines, one shift packages between 100,000 and 300,000 cartridges. Individual factories operate 3 shifts 24/7, especially during periods of high demand. One packaging machine's output reaches 12,000 units per hour. In workshops with powder, primers, and explosives, there's anti-static flooring. This is special surfacing that channels electrostatic charge from human bodies or equipment into the ground to prevent sparks. Workshop humidity is also maintained at 40 to 60%, which reduces ignition risk. Workers wear special suits made from natural fabrics or anti-static materials. Wearing metal objects, watches, or jewelry is forbidden. Only certified specialists are permitted near powder or primer zones. Access is, naturally, biometric. People don't touch powder manually. Everything happens through sealed automated systems. Primer formation, explosive mixture dosing, case sealing, everything's maximally automated. Every 45 meters, there are powder extinguishers and sprinkler systems positioned. Personnel undergo mandatory drills every 3 to 6 months. All cases, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they're disposed of or recycled. The factory is guarded like a classified facility. CCTV, armed security, inventory of every single unit. In 1998, in the United States, a powder manufacturing plant for sporting ammunition exploded due to storage regulation violations. The blast force was equivalent to several tons of TNT. 4 workers were killed. Investigation revealed dozens of systemic violations. That's why safety at such factories matters more than the products they manufacture.